The Hadoop Distributed File System, a storage system for big data. As the storage layer, the Hadoop Distributed File System, or the way we call it HDFS, serves as the foundation for most tools in the Hadoop ecosystem. It provides two capabilities that are essential for managing big data: scalability to large data sets and reliability to cope with hardware failures. HDFS allows you to store and access large datasets. According to Hortonworks, a leading vendor of Hadoop services, HDFS has shown production scalability up to 200 petabytes and a single cluster of 4,500 servers with close to 1 billion files and blocks. If you run out of space, you can simply add more nodes to increase the space. HDFS achieves scalability by partitioning or splitting large files across multiple computers. This allows parallel access to very large files since the computations run in parallel on each node where the data is stored. Typical file size is gigabytes to terabytes. The default chunk size, the size of each piece of a file, is 64 megabytes, but you can configure this to any size. By spreading the file across many nodes, the chances are increased that a node storing one of the blocks will fail. What happens next? Do we lose the information stored in block C? HDFS is designed for fault tolerance in such cases. HDFS replicates, or makes a copy of, file blocks on different nodes to prevent data loss. In this example, the node that crashed stored block C. But block C was replicated on 2 other nodes in the cluster. By default, HDFS maintains 3 copies of every block. This is the default replication factor, but you can change it globally for every file or on a per-file basis. HDFS is also designed to handle a variety of data types aligned with big data variety. To read a file in HDFS, you must specify the input file format. Similarly, to write a file, you must provide the output file format. HDFS provides a set of formats for common data types, but this is extensible, and you can provide custom formats for your data types. For example, text files can be read line by line or a word at a time. Geospatial data can be read as vectors or rasters, data formats specific to geospatial data. Or other domain-specific data formats like FASTA or FASTQ formats for sequence data in genomics. HDFS is comprised of 2 components, name node and data node. These operate using a master-slave relationship where the name node issues comments to data nodes across the cluster. The name node is responsible for metadata, and data nodes provide block storage. There is usually 1 name node per cluster. A data node, however, runs on each node in the cluster. In some sense, the name node is the administrator or the coordinator of the HDFS cluster. When a file is created, the name node records the name, location in the directory hierarchy, and other metadata. The name node also decides which data nodes to store the contents of the file and remembers this mapping. A data node runs on each node in the cluster and is responsible for storing the file blocks. The data node listens to commands from the name node for block creation, deletion, and replication. Replication provides two key capabilities: fault tolerance and data locality. As discussed earlier, when a machine in the cluster has a hardware failure, there are two other copies of each block that was stored on that node, so no data is lost. Replication also means that the same block will be stored on different nodes in the system, which are in different geographical locations. A location may mean a specific rack or a data center in a different town. The location is important since we want to move computation to data and not the other way around. We'll talk about what moving computation to data means later in this module. As I mentioned earlier, the default replication factor is 3, but you can change this. A higher replication factor means more protection against hardware failures and better chances for data locality. But it also means increased storage space is used. As a summary, HDFS provides scalable big data storage by partitioning files over multiple nodes. This helps to scale big data analytics to large data volumes. Replication protects against hardware failures and provides data locality when we move analytical computations to data.